For my surface tension project, I'm going to prove that different liquids have different surface tensions, and when you add soap or detergent to a liquid that has a strong surface tension, it will become much weaker. Important measurements that I used in this experiment were the mass and the length along the interface of a paperclip. I did not have a scale that measured under 3 grams, so instead I put the amount of paperclips needed to equal 3 grams and then took the 3 grams and divided by the number of paperclips that were on it. This value came out to be half a gram or 0.0005 kilograms. For the length along the interface, I straightened out the paperclip, measured it out to be 10 centimeters, and multiplied that value by 2 due to the fact that your force on the surface tension will be on both sides of the paperclip. This came out to be about 0.2 meters. Known values for this experiment is surface tension of water at 20 degrees Celsius, which is room temperature, and that's equal to 0.073 Newton per meter. I found online the surface tension of alcohol at room temperature to be 0.022 Newton meter, which is a lot less than water. And then I also found a range for the surface tension of soapy water at room temperature to be between 0.22 Newton per meter to 0.042 Newton meter. And this depends on the concentration and type of soap you use. So it could be more, could be less, and it's just really a range. Starting with my calculations for the paperclip, I drew a free body diagram where this is the end of the paperclip. You have two forces of the surface tension coming out both sides with the weight going straight down. The force of the surface tension don't come straight up. It comes out at a slight angle, but the angle is so minimum that we say it's about 0. First, we will find the max mass that the surface tension of water and alcohol can hold at the found length of the paperclip. If the maximum mass of the surface tension is greater than the mass of the paperclip, then it should be able to float because it will not put enough pressure to break the surface tension. If the maximum mass is less than the mass of the paperclip, then it should sink. So for the water, we start with the force of the surface tension is equal to the weight. The force of the surface tension becomes surface tension times length. Weight becomes mass times gravity. We solve for mass, plug in the numbers, and we get 0.00149 kilograms. That number is greater than the mass of the paperclip, so it should be able to stay on the surface of the water. Alcohol, we start with the same equation, solve it for mass, and we come out to 0.000485 kilograms. That is less than the mass of the paperclip, so it should not be able to stay on the surface. So I have a cup of water and a cup of alcohol. I have two similar paperclips that I'm going to try to place on the surface of each liquid. Let's see what happens. After placing each paperclip on the surface carefully, the paperclip on the water stayed on the surface while the paperclip in the alcohol sank. This agrees with my calculations. Since we don't have a certain surface tension for the soapy water, I will find the surface tension needed to hold up the paperclip. So we start with the force of the surface tension is equal to weight. Force of the surface tension becomes surface tension times length. Weight becomes mass times gravity. We solve it for the surface tension and then we plug in the numbers and it comes out to be 0.0245 Newton per meter. So if the paperclip sinks, then the soap dropped the surface tension below 0.0245 Newton meter. If it stays on top, then the surface tension is still above 0.0245 Newton meters. Here I have a toothpick that I soaked in soap. We're going to place it in the cup that has the paperclip floating in the water. Since the paperclip sink, we can assume that the surface tension of the soapy water is most likely less than 0.0245 Newton per meter.